ՂЫЛЫМИ podcast. Today we'll speak about the supercapacities and how they applied and what the future of our supercapacities. So, dear guests, our guest today is Professor Ali Chorу from University Sakarya. Nice to see you.
Nice to see you.
This is the Faculty of Science and Engineering. And let me ask you about first about the convenient capacities. Yeah? What is that? How the convenient capacities work?
Conventional capacitors work very easy, very simply because they are simple devices, and there are two plates. These plates are conductor plates, mostly metal plates, and there is also insulator medium between these two plates. And when you apply potential between these two plates, the plates accumulate charges on them. So energy is accumulated there, and electric field occurs between these two plates. If you don't use extra insulator, dielectric medium, we say, these plates has their basic capacitance, but we use insulator, or in another word, dielectric material, to increase the capacitance of these plates and to increase the energy per volume of these capacitors. These are basic materials. The property of this plate, these capacitors, is they are charged very rapidly, but they are discharged also very rapidly. This is
so in conventional capacitors, insulator, it's a typical dielectric.
Yes, it is
dielectric
material.
For example, paper
or rubber or something. Some insulator, any insulator can be used in this type materials.
Okay. So next question: what is supercapacitors? How supercapacitors work?
Yes, supercapacitors are different. They look like sometimes somehow to batteries. For example, especially we know the lithium-ion batteries nowadays. They look like their structure because they include electrolyte inside. And here we don't use insulator media. We have separators, but it is not insulator.
It's not dielectric.
Yes, it is not dielectric. Yes, it acts as filter, but not as dielectric. And here we use between two electrodes. We use solution, electrolyte solution. It is better to say. For example, mostly we use sodium hydroxide in these materials, and like in the batteries, this sodium hydroxide ionizes to plus and minus ions. So these materials, the supercapacitors works with the electrolyte system.
So, as I understand, so if we compare conventional capacitors and supercapacitors, so supercapacitors don't have dielectric, and they should show high density charge.
Yes.
And quick discharge. Yeah, is it right?
No, supercapacitors. Yes, you are right. supercapacitor has high density charge, and yes, they discharge and charge not fastly, slowly than the normal conventional capacitors. This is the advantage, mostly their advantage, because they act as the battery. For example,
not exactly as a capacitor, but more like battery.
Battery, yes.
Okay, okay. So the next question. So how supercapacitors work?
Yes. In the supercapacitors, there are two main points in their work. There are two main points. One of them is the surface of the active surface of the supercapacitors electrodes. It must be the surface must be electrolytically active, and the other one is the amount of the surface, active surface. And because of that, we use porous materials, and porous materials includes much more active surface than normal surface, non-porous surface. So we can compare this and understand this like globe. The normal surface of the globe is like our hand, but if we calculate each globe surface and if you accumulate them, total surface is much greater than the grapes own outer surface. So in the grapes, each grapes, there are much more surface than the outer surface. So, or we can compare it to our lungs. Our lungs has
like alveoles.
Alveoles.
Yeah, they have a very
very big
surfaces.
So porous surfaces are
it helps us to exchange by oxygen and CO2.
Yes, like that. In the capacitors, supercapacitors, the porous medium has much more active medium than a normal surface. So yes, and here they don't give any charge, and they don't make charge exchange here. They only coincide to each other and come together, but they don't make any exchange. And they make two surfaces here. These are known Helmholtz surfaces. And one of the surfaces is, if the one of the surface is negative layer, the other one becomes positive layer. But they don't change, they don't take together. They
because
become
the barrier
very close. Because, a barrier occurs, but this barrier cannot be seen. This is a chemical barrier only. They don't make any compound. They come together to each other. They become layer, one layer, negative layer here, and one layer here in the electrolyte. They become together, and when you discharge them, all the charges come together here, negative, positive, and positive, negative in the other side. In the cathode, negative charges come to the cathode, but positive charges come to the anode. Two layers here, Helmholtz layers. When you want to discharge it, when you use the capacitor, this negative charges goes from here to from this positive side to negative side, and positive charges goes from negative side to positive side. Here in this working procedure, it looks like batteries, but in the batteries, the charges ions make compound, and they make the electrolyte becomes ionized, but here there is no ionization. And
because all charges on the surface of electron.
yes, and
Like in the picture in the slideshows.
yes, it is like here. So here, as you see, they don't make any compounds, so it gives them so many life cycles. Much comparing to the batteries, they have much more life cycle.
Okay, so the between them there is no charging media.
Yes.
Okay. So the next question. So what sort of material usually used to construct, to design typical capacitors?
In the typical capacitors, we use metals, good conductive metals. For example, copper, aluminum, and
like electrodes.
Like electrode as electrode, and we use dielectric material between
them.
electrodes. Yeah. So
like paper, like
rubber, and ceramic
oil.
material and oil.
Yeah.
Ceramic material sometimes we can use. And if you want to make a better capacitor, we use better insulator. And small capacitor, we use better insulator. And to metal surface.
And sometimes it could be also multi-layer.
Multi-layer, like here.
Yeah.
Yes, sometimes you can use multi.
Okay, so what kind of these magic materials we use in supercapacitors?
Yes, there are many materials. For example, as seen here, and there are also we can use graphene, graphene, and
There is some magical polymers.
polymers.
Yeah.
Yes, conductive polymers,
Yeah.
and graphite, carbon nanotubes. But there is some other materials as we use perovskite oxides. These materials are new materials, and they had previously some disadvantages, but nowadays these disadvantages are managed to get rid of. So they are used more effective in this area.
So the perovskite material, it's some magic material. How it's produced? Can you say something about the production and what is that material particular?
And
Why it makes so magic to use in supercapacitor?
yes, they have lanthanides in the outer. Yes, they are cubic materials. There are lanthanides in the outer sides of cube, and there is a transition element of 3D, 4D, and 5D orbital transition element between these lanthanides, and they are electric. They are not very active electrically, but they are magnetic. They have magnetic properties. Some not very strong, but magnetic, partly magnetic.
Because
materials.
of spacious d-electronic orbitals.
Orbitals, because of their orbital structure.
And how they produce?
And there are many
It's a
methods.
synthesis.
Yes, it's synthesis. There are many methods to produce them. We say top-down and bottom-up methods to these methods. We use usually bottom-up methods. And we take the powder of lanthanide salts, and we use the transition metal salts, and we combine them chemically. We produce it, and we put them into oven, and we evaporate it, so it becomes a jelly material, and then we put it more heated oven, and we don't have any restriction about the oxygen, because there are oxide material, perovskite oxide material. We need oxygen.
You can use in simple lab
and simple
in
oven.
the presence of air.
Yes. We don't need any vacuum.
So the crystal structure looks like this.
Yes, here, and we take them to take the to evaluate this crystal medium. We put them into oven, and we heat them up to 800 degrees. Then we put them to be cool down for a long time. And they crystallizes in the long time. Then we make compression and plates. After that we use them.
Okay. So the next question. So how using these magic materials like perovskite, how you produce supercapacities? What is the structure? What is the design?
Design of supercapacitor? Yes. Actually, it looks like the batteries. One electrolyte here, the other electrolyte. Sometimes we use same type of electrolytes.
And what kind of electrodes we use? It's a metal?
No. Perovskite oxide.
Perovskite oxide, it's an electrolyte.
Electrode. Sorry. One electrode here, where these electrodes are peroxide oxide electrodes. And between these two electrodes, there is electrolyte, sodium hydroxide, and there is a separator, barrier, separator as a filter. So
it's
very
a
simple
membrane.
Membrane, yes, it is membrane, and it looks like in this manner. It looks like a battery, but there is membrane between, and this structure doesn't ionize. The positive. The electrode doesn't ionizes. In the battery, cathode and anode makes compound with electrolyte, but here no. Because of that, the supercapacitors has very long life cycle. As I said, for example, a battery can have 5,000, at least 10,000 life cycle, charging cycle, but in the supercapacitor, 1,000.
And because electrolyte not ionized,
yes,
so we have a high density charge on electrodes.
Yes.
Okay. So how it works, supercapacity? For example, how supercapacity is used for water splitting, for producing hydrogen.
Supercapacitors actually are used for supplying, depositing energy, electricity energy. But
for example, like a solar
solar cell, and from wind energy, and from any other sources. Yeah. The power plant changes, but the supercapacitors are thinking to be the future energy deposition systems instead of batteries,
because they could accumulate very high
density in very short time. Nowadays, we are using electricity cars. For example, you are going to gas charge station. It takes half an hour, and you can charge up to 7%, 70%. But with supercapacitors, if we use, we will use also, we are using nowadays. When we use supercapacitor instead of batteries in the cars, it will take only 2 minutes, maybe 5 minutes, up to 90%, not 70%. Up to 90% charge, it will take 5 minutes, 3 minutes, 5 minutes. But when we use the energy, they will have high density energy like batteries. When we use the energy, they will discharge slowly, like batteries. This is the major part of the supercapacitors comparing the other capacitors and the batteries.
They could accumulate rapidly,
Rapidly,
but discharging slowly.
Slowly because of the electrolyte and barrier.
Okay, okay. So there is some conventional construction to use solar cells for electrosplitting and so on. Is it possible to directly use like photoelectrical cells as electrodes?
No.
No.
Like this, photovoltaic cells are used energy supplied in the basic electrolyte system and the basic electrode system water splitting. And here the energy supplied energy for producing hydrogen is more because you are giving potential and you are breaking the structure of the water and you are separating it to the oxygen and hydrogen, and you need much more energy comparing to the photoelectrochemical cell. In the photoelectrochemical cell, you are using a surface, photoelectrode surface. Yeah. When the light comes to the surface, the electron irradiated and it changes its position. When it changes, the electron changes its position, the hole occurs its position, positive hole. And that positive hole attracts the oxygen from water. In the other side, there is a negative hole and negative electrode. So that negative electron attracts to the hydrogen. So you use sunlight instead of the electrical energy. You use also sunlight to break the structure of to weaken, we can say. First, you are weakening the structure of the water, and then when you apply energy, you need much less energy comparing to the photovoltaic directly splitting of the water. You use maybe 10% energy to split in the photovoltaic cells.
Okay, so in fact it's applicable. Yeah.
Yes.
Yeah. Okay. So and can we talk about the near future?
Yes.
Just pretend that supercapacitors could be applied for some application in the near future. What kind of application it could be?
Actually, supercapacitors, like this structure of the supercapacitor can be used water splitting also. But here we don't use electrolyte, we use water. We use two electrode and a porous material, and we put water inside. And when we apply short voltage, and the one side becomes positive, the other side becomes negative, like the supercapacitor working system. But here, the medium is very porous, and the water molecules are in this porous medium,
penetrate to
the porous medium. So they are in a very high electromagnetic field. There. And the structure, because in the medium there is capacitive, this medium is capacitive medium, and their structure becomes much more weakened than to compare the other all electrolyte systems. So when you use perovskite oxide electrodes to make water splitting, you use very less energy. But there is, unfortunately, and the scientists and the chemists, everybody is working on this system. Here, the electrolytes are weak in this system because they are getting damaged. And so, because they are not very stable in this water splitting process, they are not very stable. So the system gets damaged and ruins in time. Nowadays, the scientists are working. How can we cover the surface with a very thin but very
protective layer?
How can we cover the layer of the surface of the electrodes? Perovskite electrode. If when we manage it, we will manage it.
So it protects perovskite, and then
yes,
it
we will
could be
use
stable
it. Yes,
for a long
we
time.
will be, yes, we will use it for a long time.
Okay, very good. So just let us imagine possible, for example, use of hydrogen for water splitting system by means of supercapacities. As I know that the conventional electrolysis to produce hydrogen is very energy consuming.
Materials, yeah.
But you say using supercapacities, it's a very low energy consuming process.
Because
So it could be very commercial application in this case to produce hydrogen.
exactly.
So can we heat up our homes, houses, for example, especially in the Atırau cold winter?
Yes, exactly. I can say that the supercapacitor system to produce water splitting, and or in another word, perovskite oxide system for using perovskite oxide system using for water splitting will be the future of the energy production, especially hydrogen production, and it will be the future energy system of our homes. And in this manner, we can say that the Atırau is very lucky. We have river and fresh water, and because the salt water is problematic, you have chlor element in the salt water, so you have to get rid of it, purify it first, and it is expensive. But you have river in Atırau, we have river, and we have wind. Always wind. We can use.
We have the sun.
We have the sun also. We can use wind turbines to produce electric energy. We have sun, and
You know about our wind now.
and we have also sun, and we can produce the combined system here, and we can add the hydrogen production system to them, and Atırau can be very rich.
Splitting using supercapacitor.
Yes.
Okay, okay. Dear Ali Bey, thank you very much for your talk about the future energy using supercapacities. Çok teşekkür ederim.
Ben teşekkür ederim. Thank you very much for your conversation. I am very happy.
and
being here.
I wish you successful stay in Atырау, and as well as very successful research in your very interesting field.
Thank you very much. I am very happy to meet with you. This is my honor.